Alright, here we go with part 2 of how to learn the chain rule. Okay, so I had written down the rule in my first video, and I want to go ahead, just so that it's handy and we're looking at it, I want to go ahead and write it again. So the chain rule is the rule that you would apply to a function of the form y equals u to the power n, where the u will be probably a function of x, a formula that involves x, or it could be involve another variable, whatever, but the u is some other formula, some other function. And the derivative of this sort of thing is n times u to the power n minus 1, then times du over dx, where the du over dx is the derivative of u with respect to x. Okay, you might also think of that as u prime. So there's our rule. Now I want to work some problems in this video that are a little more difficult than what we would have seen in the first one. Okay, now this one is not more difficult than the ones we would have seen in the first one, but we need to agree about how to do this one in order to do this example, which is a little more difficult. Okay, anyway, well, let's see. Function is x plus 1 to the third power. So far that is like this. It's x plus 1, that would be like the u, to the third power, that'd be like to the n. It's a function raised to a power. And I want f prime. F prime is a notation for the derivative. This would be the rule to find that. Now, alright, f prime is, let's see, bring the power down, 3 times u, which is x plus 1 in this case, subtract 1 from the power, that becomes 2, and then what goes here is du over dx, or it's the derivative in this case of x plus 1, but that would just be 1. So that's how this rule plays out for this initial function. Now it's like, obviously I can express the answer to this simpler. I don't need to write the 3 and the 1 separate. 3 times 1 is 3, so 3 times x plus 1 squared. Okay, and so there's my derivative. Now I would need to know that to do this problem. The derivative of x plus 1 to the third power times x plus 5 to the fifth power, because x plus 1 to the third power is part of this. Okay, and so we know how to do that now. Now the derivative of x plus 5 to the fifth power on its own wouldn't really be any different than this. All right, but we would have to know the derivatives of these two things individually to find the derivative of this entire function. The reason is because this is a product. Okay, it's the product of two functions, right? It's x plus 1 to the third, that's one function, times separately x plus 1 to the fifth power, x plus 5 to the fifth power, that's another one. It's a product of two functions. So in that case we use the product rule. All right, product rule says if y is one function f times another function g, then the derivative of that is f prime, meaning the derivative of that first function, times g, the second function the way that it is, plus g prime times f, the derivative of that second function times the first function the way that it is. So I'd have to do that, but the way that I would find the derivatives f prime and g prime along the way here would be by the chain rule as I showed you up there. Okay, so let's try to do this one with all of that in mind. Okay, so f of x is here. I want to find f prime. All right, so here's f prime. Derivative by the product rule, the first times the second, plus the derivative of the second times the first. Okay, derivative of that first function is 3 times x plus 1 squared. Okay, times the second function, x plus 5 to the fifth power. Okay, so that's f prime times g. That's the first part of the product rule. Then plus, right, g prime. So what's the derivative of x plus 5 to the fifth power? That really wouldn't be any different than working this one out. Okay, but the derivative of x plus 5 to the fifth power is 5 times x plus 5 to the 4th power. So that's g prime. And then times f. Okay, so there it is. There's my derivative. I used the rules the way they're supposed to be used. That's the derivative. If so, you know, if this was a revenue function, this would be the marginal revenue. Okay. Okay. Now, I guess the only other matter is, could I simplify this? Could I reduce it? Does it have to have so much stuff in it? And the answer to that is, yeah, I could actually reduce this. So it's kind of, here's an analogy. Could you reduce somehow, let's say like basic algebra problem, a squared times b to the 5th power plus b to the 4th power, a to the 3rd power. So it's something like that, able to be reduced. So yeah, you could factor it. You could reduce it that way. Like, so for example, like each of these two terms has a common factor of a and b. In fact, like the most a's that you have in common are 2, right? Because this has 2 a's and this has 3, so there's 2 in common. And the most b's you have in common is 4, because this term has 5 and this term has 4, so you got 4 in common. If I factor that out, I'll get b. Take away 2 a's and 4 b's, that'll leave me 1 b left over, plus, okay, and then if I take away 2 a's and 4 b's from this one, I'll get that. I'll get a left over. So we could do something like this, and at least get it a little simpler. Okay, so let's try it. So here's on our road to the simpler form of our answer right here. So okay, I could factor out 2x plus 1s, because I've got 2 here and 3 there. And then I could factor out 4x plus 5s, because I got 5 here and 4 there. Now, besides the 3, like 3 is not common to each term, and in the 5 is not either, so I have to leave those. But from this first term, 3 times x plus 1 squared times x plus 5 to the 5th power, if I take out 2x plus 1s and 4x plus 5s, I'll leave behind a 3 and an x plus 5 to the 1st power. Okay, so that's what's left in this first term if I take this away. And I got my plus here. So again, with this second term, if I take away 2x plus 1s and 4x plus 5s, what's going to be left over? I'll have a 5, and I'll have 1x plus 1. Okay, alright, so that's the kind of thing that I was wanting to do. It's like this, really. Now, it will simplify a little bit from here. Okay, so I did this factoring part thinking that that would lead me somewhere. And where it leads me this time is that, well, this stuff in here can be combined. Okay, now I don't want to rewrite this whole thing just for me to tell you about this part. But this part and those terms can be combined and reduced and simplified. Like if you multiplied the 3 through there and multiplied the 5, then you get something that looks like this. 3x plus 15. Okay, that would be that part. And then over here you get plus 5x plus 5. Okay? Alright, and then so yeah, we could do some combining across the board in there, right? We'll get 8x, 3x and 5x, plus 20. Alright. Now, this will probably be good enough for my math lab. Okay? I mean, I cannot say that all the time, everywhere that you're doing your homework or your practice, that the answer will always be acceptable in one way or the other, but I think that this will probably be fine. And we have x plus 1 squared, x plus 5 to the 4th power, and then we said all this reduces to 8x plus 20. Okay, so that's probably okay. So I'll give you this as my answer. Now, you know, I'm not 100% certain that this will be acceptable because there is one more simplifying thing that you can do. Like, for example, you out of these two terms, 8x and 20, we can factor out a 4. Right? Because, you know, 2 times 4, that'd be 8, and 5 times 4 is 20. So, I mean, that's one more thing that might be necessary. So I'll show this to you. And, you know, I don't really know what's acceptable all the time, everywhere, like I said. But, you know, let's say if I factored out 4, then I would get 2x plus 5, right? 4 times 2x, that's 8x, and 4 times 5, that's 20. And then I would have it out here like that. Okay. So I'll give you both of them just to hedge my bets a little bit. Okay, so try this if you want to. And if you find that's not working, it's just because there's some extra factoring, some extra reducing that we can do. Okay. Now, that's how that one would work with some possibilities for example.